June 7, 1940, at Chrysler headquarters in Highland Park, Michigan. A 7-minute phone call opened a pivotal problem. William Knudsen, who had just been given responsibility for industrial production by President Roosevelt, asked a simple but bold question. Could an automobile company build a tank? The man on the other end of the line, K.F. Keller, Chrysler's chief executive, answered bluntly that he had never seen a tank before. The context at that time, the U.S. Army had only 66 medium tanks. Meanwhile, Germany had deployed more than 3,000 Panzers across Europe for over a year, using coordinated armored formations to conquer Poland in 26 days and France in 6 weeks. Given that situation, the American tank force risked rapid defeat if the war expanded. The two men did not yet fully imagine the consequences of the conversation, but within 9 months, Chrysler would do something that government arsenals had never done: convert a battlefield device weighing tens of tons into a product that could be manufactured industrially, reaching a peak rate of 1 vehicle rolling off the line every 55 minutes. This process changed every assumption about military production and demonstrated the ability to mobilize civilian industry for war. The root problem was clear in June 1940. America lagged in combat capability, even ranking behind many small countries. The Army still relied on World War II-era production methods. Tanks were hand-assembled in government workshops, each one a custom hand-built product requiring skilled craftsmen. Rock Island Arsenal in Illinois, at full capacity, produced only about 3 M2A1s per month. Each took roughly 12 weeks from receipt of materials to completion. In Europe, although Germany also used hand methods, it had begun clandestine rearmament in the mid-1930s, so by 1940 it had the capacity to produce about 1,400 tanks a year. At the same time, Britain, while more mechanized than the United States, managed only about 1,000 a year. Immediately after the call, Keller summoned B.E. Hutchinson, chief engineer, and Frank Zeter, vice president of engineering. Within an hour, the three of them met in Keller's office. The Army set an almost impossible demand: 1,000 medium tanks in less than 18 months, and Chrysler would have to build factories' design processes and deliver completed vehicles starting from zero experience in tank production. Hutchinson asked plainly about the current production time. Zeter replied that Rock Island made 3 M2A1s per month, assembled by hand with many manual adjustments. Simple arithmetic showed that if they kept that method, it would take hundreds of years to finish 1,000 units, while the Army expected them in 18 months. Keller made a decisive decision. Chrysler would not build tanks the Army's way. They would do it their way. If the Army wanted 1,000 in 18 months, it would have to accept automobile production methods, and to do that first, they needed to see with their own eyes what they were going to build. Within days, the trio went to Rock Island to observe firsthand. Workers fitted each armor plate by hand, adjusted tracks by feel, and machined each part to make up for mismatches between components. The existing M2A1 weighed about 19 tons, mounted a 37mm gun, and required roughly 8,000 separate parts, each manufactured with wide tolerances, so they had to be hand-fitted during assembly. No two were identical. Keller summed up the problem: it wasn't industrial production so much as hand carving. That method could not be scaled quickly enough to meet demand. They returned to Detroit and formed an internal working group called the Tank Committee for short assembling Owen Skelton, and experts in tooling, metallurgy, and logistics. The group met daily, working through the night in a conference room at Highland Park. The crucial breakthrough lay in how they reframed the question. Instead of asking, "How can we make tanks faster?" they asked, "How can we make tanks differently?" Skelton framed the issue very clearly with a practical comparison. An average automobile weighed about 2,000 pounds, was assembled from roughly 5,000 parts, and at Highland Park they were producing thousands of them every day. A tank weighed many times more, about 30,000 pounds, and had nearly 8,000 parts. To him, the difference lay only in what was being assembled. That perspective changed the entire approach. If you regarded a tank as a complex mechanical system analogous to an automobile, then the principles of mass production could be applied, but that required redesigning everything from scratch. Each part had to be engineered for large-scale manufacture. Assembly operations had to be organized on a moving line, and quality control had to shift from manual judgment to clear measurement standards. The team analyzed the M2A1 and found that much time was wasted on hand-fitting and truing up individual parts. Parts made to military standards at the time had large variances, forcing workers to adjust continuously during assembly. Hutchinson proposed a step forward: produce components to the tight tolerances of the automotive industry so they could be mated without hand-fitting. Chrysler's idea made many military engineers uneasy. They worried that automobile-level manufacturing, meaning parts machined very precisely in quantity, might not withstand the brutal conditions of the battlefield. They also opposed welding the hull in place of traditional riveting because of concerns about durability when struck by projectiles. Moreover, the idea of using a large moving assembly line to speed production raised questions about quality control. How could one ensure every vehicle met standards when produced at high speed? Finally, implementing the new method required investment in new machinery, finding and converting many suppliers, and setting up an entirely different quality inspection system, tasks not easily accomplished in the short term. If parts were machined accurately enough to be installed simply by bolting, labor time per vehicle would fall dramatically. Instead of a group of craftsmen around one static vehicle, measuring and modifying as they went, each part could be made identical and assembled as quickly as a standard module. Skelton went one step further. Rather than multiple workstations clustered around a single static vehicle, he called for a moving line that brought the work to stationary workers, each performing a single specialized operation. By November 1940, the team had finalized a new plan, shorthand, the Chrysler method. The core idea was standardization, and pre-machining key parts were machined on machine tools to tight tolerances so that when they reached the line, they could be fitted without hand adjustments. Armor plates were designed to be interchangeable. Hulls were welded using production jigs instead of hand fitting. Turrets mounted on standard rings, and the drivetrain used as many off-the-shelf automotive parts as possible. Everything was organized on a moving line with dedicated stations. At the same time, Chrysler won a contract to build a dedicated plant designed by architect Albert Kahn, according to the principle of the factory as a machine, one-way material, flow, open space for a line nearly a quarter-mile long, and specialized shops for machining, welding, and assembly. The plant was planned, built quickly, and equipped even while interiors were unfinished. Keller even decided to begin assembly in the unfinished building to meet the schedule. In the shop, engineers confronted a series of technical problems. A major obstacle was the drivetrain. The M2A1 gearbox had been designed for hand assembly. To adapt to the line, Chrysler engineers redesigned it into a modular unit that could be fully assembled off the line and then attached to the hull as a single component. The redesign cut assembly time from 40 hours to 4 hours. The vehicle's suspension, the load-bearing system that let it traverse rough terrain, also had to be redesigned from the ground up. Chrysler engineers decided to break the suspension into standard subassemblies, then build specialized jigs to assemble and test those sub-assemblies before installing them on the hull. As a result, a complete bogie assembly could be built in about 2 hours and mounted to the hull in roughly 20 minutes, a speed manual assembly could not match. The armored hull presented the greatest challenge. Previously, armor plates were joined with rivets. Each rivet joint had to be drilled, located, and set by hand, a process that took weeks and created many fundamental weaknesses rivets could shear in an impact, sending metal fragments into the crew compartment. Chrysler proposed an alternative weld the entire hull. At first, the Army strongly opposed. Welding could create thermal stresses that weakened the metal if not properly treated, and welding required skilled labor. Chrysler answered with evidence. They carried out a series of ballistic tests on welds, showing that in many cases welds were stronger than riveted structures. They developed heat treatment procedures to eliminate concerns about stress. At the same time, they designed precise locating jigs so workers could follow instructions to produce acceptable welds. The result was that semi-skilled workers could meet the standard after about 2 weeks of training. On schedule by March 1941, component production began. Parts manufactured in many different shops would be brought to Warren for final assembly in April. However, another problem required a creative solution: the engine. The M2A1 used a Continental R975 radial aircraft engine, a 400 horsepower radial reliable but not available in sufficient supply. Chrysler needed a fast alternative. The solution sprang from the simple but bold idea of engineer Harry Wilson. Chrysler was developing an inline 6-cylinder engine of about 115 horsepower. Wilson proposed coupling 5 such engines together into a single unit. On paper, it sounded like a mess. Linking 5 independent engines to drive a single output shaft was a major engineering challenge, but the engineering team accepted the problem. Under Wilson's direction, they created the multi-bank A57 engine. Essentially, the A57 married 5 6-cylinder engines arranged around a central gear housing. Each engine transmitted power through a gear that meshed with the output gear. The result was a 30-cylinder assembly with a rated power of about 425 horsepower and an actual total output of roughly 370 horsepower. In size and appearance, it was an oddball design unprecedented, but it solved key problems. It used available parts and technologies, required no special materials, and could be assembled by a newly trained workforce following clear instructions. The Army initially sneered, calling it a Rube Goldberg contraption, a ridiculous solution, but could not deny its effectiveness for production speed. On April 12, 1941, even though the Detroit arsenal was still unfinished, an M3 produced by Chrysler was completed on the assembly floor. The M3 was a step up from the M2A1. It weighed about 28 tons, carried a 75mm gun mounted in the hull, and a 37mm gun in a rotating turret. Although the design was not perfect, a compromise between old technology and the Army's urgent production requirements, the M3 had an undeniable milestone. It was the first tank in the world assembled on an automobile-style production line. The handover a few days later was staged as a spectacle. On April 24, 1941, the M3 drove out of the plant before a crowd of officers, industry leaders, local officials, and workers. On the test range, the tank accelerated, breached obstacles, and fired to demonstrate that mass production did not mean diminished combat capability. But the key point was what few saw behind the vehicle was an entirely new production system. The assembly line began operating. Component production accelerated. The supplier network was established. Hundreds of new workers learned the specialized tasks. By May 1941, output reached 1 tank every 2 days. By June, 1 tank per day rolled off the line. By July, 2 tanks per day became normal. Running in parallel with ramping up production was the effort to build a supply chain. A tank required about 8,000 components. Chrysler could not do everything alone. B.E. Hutchinson was tasked with developing the supplier network traveling across Michigan and neighboring states to ask a simple but mandatory question: we need parts made to these specifications in these quantities and on this schedule. Can you do it? Many suppliers initially balked, but Hutchinson offered technical assistance, advanced money to buy tooling, and guaranteed contracts as incentives. The supplier network gradually expanded throughout 1941, eventually covering more than 400 companies in 32 states. A foundry in Pennsylvania produced gearbox housings. Machine shops in Wisconsin made track pins. A forge in Ohio supplied armor plate. The workforce conversion process proceeded alongside supply chain development. In June 1940, Chrysler did not have a single worker experienced in tank manufacture. By August 1941, the Detroit Arsenal plant had become a true city of steel with more than 500 to 800 workers. Most of them had never even touched a tank before. Many were farmers, store clerks, or civilian mechanics. Chrysler had to open its own training classes right inside the plant. Each new worker was thoroughly trained for a specific task. The person installing the gearbox mounts had to practice on simulators for 2 days straight before touching an actual vehicle. This method allowed the company to absorb a massive workforce without slowing progress. Productivity remained stable, and within a month, by September 1941, Detroit Arsenal was producing 4 tanks per day. Meanwhile, the M3 Chrysler's first tank model began proving its worth on the North African battlefield. The British Army, receiving the tanks through the Lend-Lease program, nicknamed it the Grant, after General Ulysses S. Grant. They praised its durability and reliability, though they still complained that the hull was too tall and the main gun, mounted on the side, limited its firing arc. Even as the M3 entered combat, Chrysler's engineering team kept improving it. They knew well that the M3 was only a transitional step, a temporary solution between old designs and new demands. The biggest issue with the M3 lay in its side-mounted gun, which made the vehicle tall and cumbersome in combat terrain. At this point, Chrysler and the Ordnance Department began designing its successor, the legendary M4 Sherman. The M4 inherited the chassis and suspension of the M3, but featured a fully rotating turret and a centrally mounted 75mm gun. It was the first American tank designed entirely for mass production. The transition from M3 to M4 went smoothly. Instead of stopping the line to change tooling, the factory simply phased in new components while completing existing contracts. By February 1942, the entire line had switched over to producing the M4 Sherman. Chrysler's engineers fine-tuned every detail to optimize for industrial production. The hull was cast or welded from large sections to reduce manual assembly. The turret was cast in one piece in a dedicated foundry. The drivetrain used standardized interchangeable components. Even the tracks were redesigned for faster production. Then, on December 7, 1941, the attack on Pearl Harbor changed everything. America officially entered World War II. What had been a controlled acceleration effort now turned into a life-or-death race. Overnight, the demand for tanks multiplied. The figure of 1,000 units, once deemed unrealistic in 1940, was now far too low in 1942. Chrysler reacted as if it had been waiting for this moment. The factory that produced 4 tanks per day in September 1941 was turning out 12 per day by March 1942 and 18 per day by July that year. That pace did not come easily. Bottlenecks appeared everywhere. A shortage of skilled welders slowed hull fabrication, so Chrysler opened its own welding school, graduating 50 certified welders each week. When machine tools were scarce, they negotiated directly with manufacturers for delivery priority. Owen Skelton, now serving as executive director of production, established a new system called production expediting, meaning accelerated production. Engineers constantly monitored the floor, identifying issues within hours and resolving them within days without waiting for paperwork. Production discipline at Detroit Arsenal became almost obsessive. Daily output numbers were posted publicly. Every worker knew how many tanks had been built that day, and each shift wanted to outperform the last. Then, in December 1942, Detroit Arsenal achieved what no one thought possible: 896 Sherman tanks delivered in a single month. That meant an average of 29 tanks per day, faster than the combined total of all other American tank plants. Detroit Arsenal alone produced more than the entire tank industry of Nazi Germany. This achievement was no miracle, but the result of relentless optimization. The line ran with clockwork precision. Every 55 minutes, a fully completed tank rolled off the final station. Workers mastered each motion through months of repetition. Suppliers delivered parts so punctually that inventory was nearly zero, and quality inspection became a scientific process, measuring every dimension, every weld, every joint. December 1942 marked the peak of production efficiency for the entire wartime period. In the months that followed, output remained impressive, but that December record was never broken. It was proof that tank production had truly been transformed from craft to modern industry. The success of Detroit Arsenal created demand to replicate the model. The Army wanted to distribute tank production capacity nationwide. Many new plants were built, including facilities run by General Motors Pressed Steel Car Company and Pacific Car and Foundry. Each plant adopted assembly line methods and precision machining, but Detroit Arsenal retained a unique position in output and efficiency. At the end of the war, in August 1945, Detroit Arsenal logged an astonishing figure: 234 tanks of various types rolled out of that facility. That number represented about 1/4 of the United States' total tank production during World War II. But the number was only the tangible part. More important was how those vehicles were produced and continuously improved. The Sherman was not a fixed design. It evolved continuously. From the M4A1 with a cast hull to the M4A2 using 2 diesel engines to save fuel for British and Soviet service, the M4A3 fitted with the Ford GAA engine, and the M4A4 using Chrysler's multibank A57 engine. Each variant was a technical adjustment to suit battlefield requirements and the supply chain. These changes required line adjustments, but the essence of assembly moving lines, jigs, inspection procedures remained the same. That was the advantage. Changing the design did not mean retraining craftsmen from scratch. It only required changing jigs, swapping parts, and updating work instructions. The Sherman's reputation has always been debated. Compared with German Tigers or Panthers, the Sherman was weaker in armor and firepower. In one-on-one fights, a Sherman crew faced high risk. But in the broader strategic picture, the Sherman had clear advantages. It was reliable, easy to repair thanks to standardized parts, and decisively available in overwhelming numbers. The ability to repair quickly in the field and the wide supply of spare parts kept vehicles running longer than many enemy types. Looking at production numbers tells the strategic story. Germany built about 24,000 main battle tanks from 1939–1945. The Soviet Union produced about 105,000. Britain about 28,000. The United States, which began large-scale production in 1942, produced roughly 90,000 by 1945. Detroit Arsenal alone contributed nearly 25% of U.S. output, but beyond that figure was the lesson in method. Before 1940, many countries regarded tank manufacture as the province of specialized government arsenals, requiring master craftsmen and months of work. Detroit Arsenal overturned that notion. They proved that tank production could be an industrial task based on precision machining, a dispersed supply chain, and rapid worker training. The consequences were enormous. Workers could be trained in weeks rather than years. Plants could scale capacity quickly by mobilizing private industry. And even when experienced labor was drafted, production continued thanks to standardized processes. After the war, Detroit Arsenal was not immediately shut down. The plant continued to operate under contracts with the U.S. government. Initially, tank production was halted during peacetime, but it was quickly resumed during the Korean War. From 1952 to 1954, the facility produced more than 300 to 400 M47 Patton tanks for the military. Entering the 1960s, Detroit Arsenal continued building the M60 tank, and by 1979, it began producing key components for the M1 Abrams, the most advanced American tank of its time. However, by the early 1980s, financial pressure forced Chrysler to sell its defense division to General Dynamics for over $336 million. General Dynamics continued to operate the Detroit Arsenal plant for more than a decade before transferring all tank production to the Lima Army Tank Plant in Ohio in 1996. Today, the Detroit Arsenal area is no longer a tank factory, but it has been preserved as both a historic site and a modern military center. It now houses the U.S. Army's Life Cycle Management Command, LCMC, and the Combat Capabilities Development Command Ground Vehicle Systems Center. A memorial plaque in Michigan still records the facility's achievement that Detroit Arsenal produced more than 22,000 tanks and proved that America's industrial power could itself become a weapon. What deserves to be remembered is not just the thousands of tanks that rolled out of its doors, but the shift in manufacturing philosophy. A group of engineers and industrialists refused to accept the common assumption of their time that tanks were a special military product that could only be hand-built in state arsenals. They looked at the mechanical essence of the problem and saw something simple but vital. Both automobiles and tanks are systems made from thousands of components. If you break down the work, standardize the parts, and organize operations on an assembly line, mass production ceases to be impossible and becomes a technical and managerial challenge that can be solved. To achieve that, they needed more than technical innovation. They needed courage and industrial confidence. Technical courage meant daring to redesign weapons according to new principles despite skepticism. Industrial confidence meant daring to invest massively in machine suppliers and people to try a method never before attempted at such scale. The result was not a small production improvement, but a strategic shift. America's ability to mass produce became a decisive advantage on the battlefield. Without the Shermans built in such numbers, U.S. infantry forces would have been outnumbered. Britain would have struggled to replace its losses, and the Soviet Union benefited from thousands of American-built Shermans. The capacity to produce 88,000 to 90,000 tanks in just 4 years was the clearest proof of American industrial power, and nearly a quarter of that came from a single plant in Warren, Michigan. But the greatest legacy of Detroit Arsenal was not just the steel machines, but a concept proven in action that private industry could solve military problems faster and more efficiently than government arsenals. Detroit Arsenal showed that industrial engineering and organization were as important as guns on the battlefield. It confirmed that when properly mobilized, America's productive capacity could become a strategic weapon. This mindset shaped U.S. strategy throughout the Cold War, when civilian factories could convert to military production within months, and the relationship between government and private contractors became the foundation of modern defense industry. The engineers of Chrysler were ahead of their time. They didn't just build tanks, they designed an entire production system in which everything suppliers, assembly lines, workers, and quality control functioned as a unified whole. Every part of the system was created to expand, change, or improve without stopping production. And it was precisely this flexibility that turned Detroit Arsenal into a giant machine capable of doubling output simply by adding shifts, expanding orders, and training more workers. Efficiency grew exponentially. The first M3 in 1941 required 500 man-hours, while the M4 Sherman needed only 150 hours to complete by the end of 1942. Productivity increased more than 300% in less than 2 years. The culture of continuous improvement rooted in the automotive industry became the pillar that helped America win the race for armament production. The total cost of the program exceeded $100 million, but the 22 234 tanks produced had a combined wartime value of more than $2 billion. However, the true value did not lie in profit, but in the strategic advantage they provided. It was the production power of Detroit Arsenal that gave American forces overwhelming superiority in every campaign from the deserts of North Africa to Berlin. Without this factory, the outcome of World War II might have been very different. The story of Detroit Arsenal is ultimately a story about vision beyond limits. When K.F. Keller told William Knudsen that he had never seen a tank before, it was not a confession of helplessness. It was the starting point for an entirely new way of thinking. Chrysler's engineers did not know how to build tanks, but they knew how to create complex mechanical assemblies from thousands of parts, and they believed that engineering could solve any problem if organized the right way. While Europeans still regarded tanks as handcrafted works, Americans saw them as machines that could be mass-produced, and they proved it. In 9 months, Chrysler went from zero to delivering its first tank. In 18 months, they exceeded their production targets. And in just 3 years, they built more tanks than most nations did throughout the entire war. Those workers, engineers, and craftsmen never went to the battlefield, never held a gun, yet they created the tools for others to win. They were not heroes on the front line, but they were soldiers of the factory quietly changing the course of an entire war. And it was this democratization of industrial power, where ordinary workers could achieve extraordinary results, that became the true revolution Detroit Arsenal left to the world. If you find this story inspiring, share the video so more people can learn how ordinary individuals changed history. And don't forget to subscribe and turn on the notification bell so you won't miss the next stories where we'll explore more of the hidden turning points in human history.